Hello and welcome to the course Hidden Mass Transfer. This is the first video in the series of lecture videos. It's about radiation. My name is Reinhold Kneher and I'm the course responsible. Well, the learning goals are relative to radiation properties. They're understanding wave quantum duality. Then we move over to the black body, how to describe radiation from that to the Stefan Boltzmann law. Another law is Wien's law of displacement, and then apply that to objects having wavelength dependent properties. And at the end, I will present you some questions related to that lecture. Now let's move on. What is radiation? Well, from physics course, you probably have done such an experiment. A lamp was used, or let me take a laser pointer here. A lamp has been used, then a double slit was presented to the radiation from that lamp, and in the far field an observation screen was put. And we see then a sequence of stripes mimicking that slit of different intensity. So the wave explanation is we have plane waves approaching that aperture. Elementary waves emerge from the two slits. They can interfere in the far field, and if we put a screen, we can then on the screen observe an intensity distribution as shown here. And please note the dotted line, that's this here, that would be if you have one slit. If you use a double slit, you get more, you get still that central maximum. It's not as wide as with a single one, and then minima maxima to the side, which are of less intensity. Now, what happens if we use the quantum mechanics description? Well, then we assume photons are going to be shot toward that aperture. They can pass through the slit, and we will see in a video that this is the slit bars, the interference pattern, and that's the intensity. Now let's have a look at a video that was taken from a colleague in Switzerland. And they used a specific experimental setup where they could basically shoot photons at a pace that they could record that. And I need to move over to the mouse. And you see here the photons can go anywhere on that observation screen, but the likelihood that they meet where we would expect them to meet using the wave theory is clearly coming out from this image. This means the two approaches are describing the same thing. And this means in the future, just to state again, the quantum mechanical observation leads to the same result as we know from wave optics. This means we will continue with equations derived from quantum mechanics, and we will, in these equations, however, still have terms such as wavelength, frequency, wave number, just because it's established and it's very convenient. Excuse me, very convenient to move on with that. Now, the speed of light will play a role. That's the frequency times wavelength. The energy of a photon, that's what Max Planck calculated. He could draw everything back to natural constants except one property where he used a helping variable which he called h, and that's named after him. That's Planck's constant. You see here the alphanumerical value and the unit. And with that you can calculate the energy of a photon if you specify the frequency or the wavelength. So the frequency, for example, in the visible spectrum would be 10 by the 14, and still we get then a very small number for the energy of one individual photon. Now let's have a look to this visible light and wavelength separation. You see here, let's move back to the laser pointer. That's the size wavelengths ranging from very, very small, that's gamma rays, X-rays, we have ultraviolet, that's where basically our sunburn can come from, then visible, then we have the infrared, microwave, radio waves. And we are mostly concerned here, if we talk thermal radiation, with infrared waves. The visible, please note, ranging from roughly 400 to about a little bit above 700 nanometer or 0.7 micrometer. Now, when we perceive objects, for example, such a green leaf, then it's typically the reflection of that leaf. So the rest of the colors that are within the white light that is emitted by the sun here and arrives in our here is absorbed. And of course, due to its own temperature, there might be also some emission from that leaf. We will get later on to the point that this emission at that temperature that the leaves typically are is very, very insignificant compared to the reflection. Now, we will use a special object throughout in radiation, and that's a so-called black body. It's indicated here that black body is absorbing all incoming radiation. So the only part of radiation that we can perceive from a black object is what the object emits due to its own temperature. And so this radiation emission solely depends on the temperature of the body. And this black body is an ideal thermal radiation source that we use from now on as comparator or reference. And important as definition for black body, all incident radiation is absorbed. And what is being emitted is emitted over the entire wavelength range. And amongst all bodies known, a black body emits at a given temperature the maximum. Now let's have a closer look, and for this we go to what Max Planck has derived from quantum theory. He derived an equation for the distribution of the radiation intensity of a black body, and it's a function of wavelength. And here we see his distribution law. So I will explain this formula in a second on the next slide, and you see here two constants are employed, C1, C2, the values are shown here. Now, Planck's distribution law. The dot means that's a time derivative. The two primes are for an area derivation. Then the index B stands for black body. The index lambda signals that this is wavelength specific. And we see in the formula the wavelength and then a parameter T. So T is just a parameter in this one, and I'll show you how this comes out. Let's say that's the evaluation of this formula for a certain temperature T1. If I use another temperature which is lower, then I get a curve where the maximum is lower compared to the one of the higher temperature. So T1 is larger than T2, and so is the max intensity here. Now, if we put the visible spectrum in between 0.4 and 0.7 micrometers, please note this is 10 by the minus 6 meters, so it's micrometers, then this is the visible radiation, and we could get to this spectral distribution by using a prism where sunlight enters and then it's distributed into that different spectral wavelengths or colors. Now, the example from real life here is one from steel production. You see here a process where a steel bar is produced and then it's pushed to the side, and steel bars produced at the earlier time are further down, and you see that the color is changing from bright yellow to darker red here. And if I look for these colors, I can see that basically in here, whereas the darker red, I always see the maximum of intensity because our sensor, our eye is sensitive to intensity. So we see here this curve and typically the maximum emission at the yellow one. In order to provide a guideline for their workers, steel industry came up with such a heat color map. And you see here Fahrenheit or degrees centigrade for yellow down to red. And you see that the temperature then is here in centigrade is just halving between the yellow and the dark red. And what's also important, below there is a non-visible colors to us, which still indicate that the thing is damped hot and we shouldn't touch it. Now, intensity is increasing that way. Now let's have a look at Planck's distribution law, evaluating it for different temperatures here. So that's sun temperature. and irradiates almost black, so it follows Planck's distribution law. How we get to the sun temperature, I will show you in a second. That's another temperature, and so on. And we have put a red dot at the point where the maximum is. And if we go here down, we see that the red dot is shifted to larger wavelengths if the temperature goes down. And there's a physical law behind that that's called Wien's law of displacement. That's another researcher who found out that the multiple of this maximum wavelength with the corresponding temperature is a constant value. Units micrometer times Kelvin, and this describes the position of the maximum, and then we can calculate sun temperature. For example, if we take 0.5 micrometer here as position of the maximum in the wavelength area, could have taken 0.6, and then divide just the constant by that value to come up with a certain temperature. And here any value between 0.4 and 0.7 would have been fine. Now the area, so far we just looked at this curve, and if you want to know how much radiation is emitted in total by such an object, well, then that's the area below that curve. And the area below that curve means we have to integrate that from 0 to infinity, which I can't show here, so I'm stopping the graph at 2 micrometers. So it's an integral between 0 and infinity of Planck's function over wavelengths. And of course, I need to specify the temperature of the curve because that's the parameter. Now, what is the result of that? Well, the result leads to the Stefan-Boltzmann law. That's the total power emitted by such a black body, and it's sigma times T by the power of 4. How do I get there? For this, I need to go back to the mouse pointer. Well, you need to do a substitution. The substitution is to put in an x for lambda t over constant C2 to derive their d lambda and other elements of the formula. If you put that in, then we first can put the first C2 that comes from the dx here out of the integral. We have a C1 t by the power of 4. Here we have this term here, and if we sort this now to have all the expressions that are not dependent on lambda, we get this and the T4 in front of the integral, and we get here an integral with x by the power of 5 and an exponential function. The solution for this can be found in mathematical tables, for example in Bronstein-Semendyaev, and that's p by the power of 4 divided by 15. So in total, this area under this curve is sigma times t by the power of 4, and sigma is this C1 over C2 by 4 times p by the power of 4 divided by 15. So that's the process how to get from Planck's distribution to derive the integral. That's the Stefan-Boltzmann distribution. And the value of the Stefan-Boltzmann constant is 5.67 times 10 by minus 8 watts per meter squared and Kelvin by the power of 4. And this is the total radiative heat flux of a black body, a black object, at a given temperature. Now let's work a little bit with that. The constant I showed you. Now let's go back here. There we looked over the entire wavelength range. Now I'd like to first show an example where radiation is only important in a certain fraction of that wavelength range. And for this we are looking at a glass window. And there's nothing spectacular at the visible wavelength range, but we will see that in the infrared something is changing. Here's our experimental setup. We have taken an image using a digital camera, and in the image we see an infrared camera, and there's a window, and the window is closed. So the infrared camera looks from the inner side to that window. And of course with our eye we can look through, we see what is outside. And now let's have a look at the image that this infrared camera was taking while it was photographed. And we see here the infrared camera sees itself, and there is the person with a digital camera that took the picture to the left. Or we can clearly see that for the infrared camera, this is a mirror. The window is non-transparent at the wavelength where this camera is sensitive, because it reports only what is behind, or it sees itself. So this is a clear wavelength-dependent effect. So the window is only transparent for certain wavelengths. And if we have to deal with such radiation, we can still employ the Planck law. And now the difficulty is, for example, that we have to calculate things only up to a certain boundary wavelength, called here lambda 1. This means now an integral has an upper boundary instead of infinity, it's lambda 1. And this is mathematically a bit more difficult to calculate, because for the one with infinity, we found mathematical tables to give us a solution. Now, on the left-hand side, this is q dot 2 prime's black body for the range of 0 to lambda 1. Now, the solution for that shall be related to the maximum possible amount. That's the entire surface area here, and that's shown, and we have calculated that by sigma times t by the power of 4. So if you want to know the fraction of radiation between 0 and lambda 1 that a black object emits at a certain temperature, well, we have to divide it by sigma times t by the power of 4 to get that fraction. You don't have to do that because we provide you a formulary at the end of our script, and that formula is just a table where the table entry is you select a value of lambda times t, and then you find that fraction. This lambda times t is the natural variable of the problem. If you ask yourself, how do I get to lambda times t now? Well, here a quick insert. If you take your Planck function and just divide it by t by the power of 5 on either side, then you get here on the right hand side the lambda minus 5 I have written down here. I get t by the power of 5, and if I put that in brackets and put the power outside, you see that the combination of lambda times t shows up here. And then for solution, the exponential function is developed in a polynomial, and there is an interesting paper that clearly and nicely explains all of that, and I'll provide this also in the learning room. And here's the quotation. If you want to look it up, you can freely download it from internet. Now let's move back. That's why we have there lambda times t, and you can use that formulary to calculate that relative fraction compared to what the black body emits in total. And if we have now an object that has a wavelength range, let's say between lambda 1 and lambda 2, the approach here is pretty straightforward. We calculate this green, so the total emission up to lambda 2. Then we calculate the red, the total emission up to lambda 1, and then we can use the principle of superposition and just take these f values from the table and subtract the red off the green. And then we get the fraction of radiation between lambda 1 and lambda 2. Just go back to the laser pointer. The same holds also if I have just one lower boundary frequency and it goes to infinity, so the integral excuse me, doesn't start at 0 but at lambda 1. Same approach, I calculate the total, I subtract the red portion of that, and I get here from a certain frequency to infinity. And that concludes my lecture today. I would like you to go over these questions and to see whether you can answer these questions with the lecture provided, and if not, please go back and have a look at the flimsies and the video again. So the questions are: what is a black body? Which assumption did I take to calculate something as a black body? And then which law did I use to calculate the wavelength at the intensity maximum of the black body? The Please have a look at the approach to derive the Stefan-Boltzmann constant, and at the end, just a practical thing, train with a table to look at radiation intensity at a certain wavelength range. Thank you.